So my main interest, my main interest in research is stochastic control and mathematical finance, and yeah, stochastic games. And now today I'm talking about deep solvers for semilinear PDEs. So you can already imagine this is not really my main area of research. But the last couple of years, there have been so many exciting results in that area that, well, I just wanted a piece of the pie. And that's why we started working in that direction. And yeah, you will see what came out of that. As you can see from this first slide here, there are quite a few co-authors to this paper. The reason is that we started it as some kind of a, I like to call it a research internship with the first 3 students and this student here. So when we started, they were master students here in Berlin, and quite good master students. And I wanted to do research with them, wanted to show them how these things work, to get them into doing research, and then hopefully at some point they will do a PhD afterwards. And this is what came out. This came out of this this little project. Frank Seifried here is a professor in Trier. He joined with a couple of very nice ideas, which improved the paper even further. That's why so many people are on that paper. All right, let's jump right in. What's the main question, or what's the motivation? Why did we start looking into this? And yeah, as I said, the last couple of years, there have been very exciting results in the application of machine learning, deep learning methods in well, solving PDEs or solving optimization problems in with stochastic interpretations through Feynman-Kac realization and these kind of things. And yeah, most of these papers in the beginning, at least, they're really just example driven. So you saw people doing PDEs in 100 dimensions, which is quite impressive. Or this increased even further. I think the highest number of dimensions of PDEs which can be solved by these deep learning methods, which I have seen at least, is something like 10,000. Imagine solving a 10,000 dimensional PDE. And these things are really cool. And at least in my opinion. And I wanted to understand why. Why does this work? Or can we get a better understanding from a mathematical point of view why this is possible, and why these things are, or why these methods, these deep learning methods, are so capable of doing these kind of features. And of course, this is a very formidable question, and we will only give a very, very specific answer to these kind of things. And there are so many open questions, but yeah, that's the direction that we're going in today. So let me be a bit more specific about the setting. I will look at semilinear PDEs. So PDEs, which for those of you doing more familiar with the stochastic side of things, these correspond to forward-backward stochastic differential equations, where the forward SDE is not affected by the backward SDE, so uncoupled forward-backward SDE. And for this, we picked a very specific kind of deep solver, so a neural network approximation of the solution of this PDE, which you will see in a second. And yeah, this method, I will explain it in detail in just a couple of slides, but essentially what you do is you write down the forward-backward SDE and then do a Euler-Maruyama discretization, and then try to minimize the error in this Euler-Maruyama discretization using neural networks. And what we can show is that if you do this kind of method, then we get a rate of convergence, which is of order 1/2 in the time discretization, which is quite nice. And yeah, most importantly, all the constants that we see showing up and all the rates, they do not depend on the dimension of the state. So on the dimension of the PDE. However, what we're not able to show is that we also have independence of the size of the underlying Brownian motion. So there is some kind of dependence on the size or the dimension of the problem involved in there, And at least in our proof, it's through the dimension of the Brownian motion. We will talk about this in more detail later. This is just what you can expect in the next couple of minutes. All right, so here's the overview of the talk. First of all, I will show you how precisely these deep solvers for semilinear PDEs work. We will see the derivation, what kind of PDE we're looking at, and all these kind of things. Then we will move on to the main mathematical results, convergence results, and then I will close with a couple of final remarks. All right, so how do these deep solvers work, or our particular deep solver? We start with a partial differential equation, which you see here. So this is a semi-linear PDE. We have a time derivative, we have a terminal condition here. This A thing that you see over here is a second order linear differential operator. And then the nonlinearity is this F that you see over here. So it depends on first and 0th order derivatives. So this is a semi-linear PDE. And the linear operator that you see here, so most of you probably are familiar with these kind of things. This is the infinitesimal generator of a diffusion process, so of a solution of a stochastic differential equation, which takes this standard form. So process X, driven by some Brownian motion W, the stochastic differential equation. Right, and now my first claim is that the solution of the PDE, so the function U, can also be expressed in terms of a stochastic process, but which is not running forward, but backward in time. And to see this, suppose that we can actually solve this PDE, by which I mean we have a classical solution, so once continuously differentiable in time, twice in space, and then we can apply Ito's formula. So we take our forward process, plug it into the solution, apply Ito's formula, and what you get is what you see here on the right-hand side. And now we can rearrange things slightly. First of all, here you see U at time capital T. And if we look back at our PDE, this is where we have the terminal condition. So we can replace U by G. So this is G of xt. And in here, we have time derivative and infinitesimal generator. And from the PDE, we know that this is minus the nonlinearity. This also comes from the PDE. So if we plug these things in, we end up with something like this. So terminal condition, integral from small t to capital T, then the nonlinearity, and well, some stochastic integral with respect to Brownian motion. And now I introduce two new stochastic processes, Y and Z. So Y is given as U evaluated at X, and Z is given by this sigma times the gradient of U. And if I do that, I can replace them in my equation above, here, here, and here. And what I end up with is this object down here. So this is a backward stochastic differential equation. So if I just write down this equation at the very bottom, you would try to solve that for a stochastic process Y and a stochastic process Z. We have specified a terminal condition, so this is the value of Y at time capital T, and then we solve it backward in time to get this entire process. So this is a backward stochastic differential equation. And in that sense, we are not looking at semi-linear PDEs, but instead we're actually looking at backward stochastic differential equations. All right. So one takeaway message from that is if you are interested in numerically finding the solution of the PDE, you could do that by trying to solve the backward SDE. Because there is this nice relationship over here, provided that we have classical solutions and so forth. So how would you do that classically? A classical approach would be to write down an Euler discretization of the forward and the backward process. So let me show you how this is done. We take our interval from 0 to t. 0 to the capital T, and we divide it in equidistant steps of length h. We write down increments of Brownian motion on these grid points, and then we just do a classical Euler-Maruyama discretization first of the forward process by freezing the integrants in the two integrals that we have defining our process, and then multiplying them either by the length of the time increment or by the Brownian motion increment. Yeah, so this is really a classical Euler-Maruyama discretization of the forward process X. And you could do, at least in principle, the same thing for the backward component. So naively, you could write down the same thing. So y at time I plus 1 should be approximately at least y at time I, and then we are freezing whatever is inside the Lebesgue integral and whatever is inside the stochastic integral, and multiplying by time step and Brownian increment. I can write that down formally. And then I could try, at least again in principle, to solve this kind of naive Euler-Maruyama scheme for the backward equation for y and z. However, what you see here is that we have one equation for two unknowns, or we have I equations for 2 plus I unknowns. So that's why I call this a naive Euler-Maruyama discretization, because you have to put in extra work to make sense of all of this. Nevertheless, this is really just, think of this as a discretization in time of this backward SDEs that you see down here. Let me remove all the orange stuff. So you discretize what we have down here in time, and you end up with this kind of equation over here. You can make all of this rigorous, writing it down properly, but this is now just to fix ideas. Okay, and now comes how does this deep solver business come into play? So we have small u, which is the solution of the PDE, and we would like to approximate that by a function capital U. This could be a neural network, but this could also be any kind of other nice approximating function that you wish to choose. And my claim is that this function capital U approximates the solution of the PDE well if and only if the Euler-Maruyama discretization of the backward component is close to our approximating function evaluated at the forward process, or the Euler discretization of that. To give you an idea why that is the case, you can see that here. So we know that if everything works out nicely, the Euler-Maruyama discretization of the backward process should be close to the solution of the backward SDE, so the continuous time object. Yeah, provided everything is nice enough. We already know that the solution of the BSDE is in fact the solution of the PDE evaluated at X. And this should be very close to, well, the solution of the PDE, but evaluated at the Euler-Maruyama discretization of the forward process. So these should all be close together, because these are just discretizations of the continuous time objects. And now suppose that we really have that our approximating function capital U is close to the solution of the PDE. Then we would have that these two are very close together, which means that this guy and this guy, they should be close together, which is what I claimed over here. On the other hand, if we suppose that these two are close together, can write this down over here, then from that I immediately see capital U and small u should also be close together, at least everywhere where X was running through.
Can I make a comment?
Yes, sure.
On the previous page, when you introduce this naive forward Euler, right? Oh, backward Euler in this case. what is really not so naive here is that Y and Z are processes that are adapted to the filtration, right? Because it depends on X. Yeah. And when you move backwards, right, it's not obvious. I mean, at least obviously you know how to fix it, but it's not obvious from this equation. And this is the first thing that comes into mind. Why the Yi and the Zi will be automatically satisfying this dependence on the past and not in the future, right? Because the information in principle as it is written is coming from the future, from Yi plus 1.
Yeah, that is a very good comment, and this is precisely how you fix this naive Euler-Maruyama. So my point here was that this equation is not enough to determine both Yi and Zi. And because one equation, two unknowns, you have a lot of solutions possibly, but you're looking for the ones which are adapted to the information at time I. This is the second condition that you impose. And if you do that in the right way, then you get a well-posed backward Euler-Maruyama scheme.
Thank you.
Yeah, so this is a very good comment. Yeah. And that's what makes it naive. And that's why I'm writing naive here, because this is far from being rigorous. Okay, and now the hope is that, well, if I have a good approximation of the PDE, if and only if my approximating function is close to this backward Euler-Maruyama thing. Yeah, so the main idea is, well, I take an approximating function u, and I write down this backward Euler-Maruyama in terms of this function u, and I try to minimize the error that I get. Right? So this was done in a paper by Raisi, 2018. So he proposes a loss functional, which you see here, of this form. Yeah, so you take your approximating function capital U. At time capital T, you want it to be close to the terminal condition. And then at each point in your time discretization, you are minimizing some squared error. Yeah, and this is what the squared error term looks like. Yeah, so to explain why we end up with exactly this guy over here, yeah, from this almost identity should be approximately Yi bar plus 1. Yeah, this guy over here is approximately Yi bar. Yeah, this F times H is actually this guy over here times H, and what you see down here is actually the Zi bar transpose increment of Brownian motion, right? Just written in terms of what is approximately, right? Hopefully, if U is a good approximation. So if you do this kind of replacement, you end up precisely with the Euler-Maruyama, the backward Euler-Maruyama scheme. Yeah? And if you minimize this loss functional, this will be close to 0, so the function U should have a very small error in the Euler-Maruyama discretization, so it should be close to Y bar. Yeah, that's the entire idea of this method. Okay. And this is how you end up with that loss function. And this paper by Raisi is so when we first read it, very exciting. So he writes this thing down and then gives a couple of examples where he solves really high dimensional PDEs with these kind of things. As approximating functions, he uses neural network, feed-forward neural networks. Sorry.
Can I make a comment on question? So if you look at the loss function, can't one also think that that the first part is penalizing essentially the departure from the value at final time, and the second one is just a residual of the PDE that you want to enforce on U capital? So it's like a pin somehow.
Can you say the last sentence again? I didn't hear.
Will one think that then the second part, the residual square that you're taking, the expectation is connected somehow to the residual of the PDE that you want to solve?
Yeah, in a sense. So this is
Because
the terminal condition that you want to hit, and this enforces the right dynamic.
Exactly, right? So,
yeah, exactly.
Okay.
Yeah. So this is very closely related to these kind of, there are certain deep Galerkin methods which look very similar.
Exactly.
You would just write down here the entire PDE, as your loss term, and ours comes from the stochastic representation of that PDE. Yeah, so it's very closely related.
Yes, once you take the expectations, right? I mean, these DWs will start connecting with H, and then you will get something that connects to the
to
the PDE.
Precisely.
Right.
Yeah, this is the stochastic view, and the Galerkin view is when you write on the PDE as your loss term.
Yeah. Thank you.
All right, and this is not the only way of doing it. This would be my next point. So this is one way of writing down a loss functional for these deep neural network approximations for PDEs. There's this deep Galerkin, which I just mentioned, where you just write down the PDE as your loss. And there are other ways to do that. So there has been quite a lot of work by Arnulf Jensen and co-authors. They do something very similar. The loss looks very similar. The main difference is that they use a different approximating function on each point in time. Yeah, so different neural network on each point in time, and then try to learn the PDE like that. I like this kind of approach here better because if you have a small loss, then you would expect that you have approximated the entire solution of the PDE on time and space, and on your entire time and space, and not just at initial time 0, which these other papers said.
Yeah.
The downside is this makes the mathematics a lot harder. So there are quite a few convergence results for these other methods where you really use on each time step a different neural network. For this kind of loss functional, we at least didn't find anything, and that's our starting point. Yeah, that's where we wanted to enter this whole business. And when we started working on that, we realized this doesn't work, or we couldn't get it to work. So the issue is that this loss term that you have over here, this doesn't lead to the right rate of convergence. We'll talk about this in more detail later. So which just causes us to write something slightly different down here. So we adjust this term only. So this is the same as before. And now we add something or subtract something on top of that. Another stochastic integral. What is happening here is essentially, in a nutshell, this is what you get when you do a higher order discretization of the backward SDE. So instead of Euler-Maruyama, something like Milstein discretization. So it's a higher order method to get a better rate of convergence. That's the entire idea. So we have a slightly adjusted loss functional. And we will see later why exactly we have to do that. The critical point here is, if you now want to really apply this, if you want to find a good approximation U, what you need to do is you need to be able to evaluate your loss, of course. And for this, you need to compute this guy over here. But in here, there's this stochastic integral. And here you have a Brownian motion, multidimensional, integrated against itself. And some of you will probably be aware of what kind of problems this can make. This becomes very expensive and can, in many situations, not be done exactly. So you would need another discretization here to get a good approximation of that last term that we just added. Luckily, however, you can make a nice transformation which allows you to actually compute the integral exactly. So there's no need for additional discretizations or anything. You can really simulate this random variable Li here. So very important point. Even though there's stochastic integral involved here. Can be done. All right.
Sorry for the interruption. Just a quick question. So when you mean you can simulate it exactly, you mean it for one-dimensional case, right? Or is it for multi-dimensional case?
Even in
because you also have to consider the Levy areas which come from the different components, right?
Yeah. So that's precisely what I was aiming at. So that's the main issue. If this here is multidimensional and you're integrating, you can ignore everything that we have down here. It's really just if you're integrating a Brownian motion against itself. If it's one-dimensional, you have a closed form expression for that, and you can just simulate, or you can draw from that from the correct distribution. But if it's multidimensional, so if you have one component of the Brownian motion integrated against the other, there's no closed form solution for that integral, and then you would need to somehow approximate that, come up with a clever idea to simulate that. Here it turns out that we can do that because of the structure of that term here. So we can make a transformation which essentially diagonalizes these integrals here. That's because essentially we have the sigma transpose here, which will be assumed to be invertible, and then we can just transform it in space, to diagonalize it, and then it works. I don't want to go into details here. The point is we can do it in our setup. It's possible.
Thank you.
But that's the main issue. So when I look at that, I would say you cannot simulate that. But it is possible. Okay. Now that's our loss function, right? This is what we want to minimize, and the question is, does that work? So if you now really go ahead, you take a nice approximating a class of approximating functions, and you minimize that loss functional that you have on top here. Will that really be close to the solution of the PDE? So does the whole method work? And if it works, do we get a rate of convergence? That's the main question that I want to answer. And well, here are the main results. First of all, I have to, of course, impose a couple of conditions to guarantee that everything is nice enough. In terms of the data of the problem, essentially I want a classical solution of the PDE. So I can write down certain conditions which guarantee that. I can be very precise on what I need for our proofs. And you will find it here. We need spatial derivatives up to order 3. We need one time derivative, and we need one cross derivative. They need to exist as continuous and bounded functions. And then certain Lipschitz and Hölder assumptions need to be satisfied, but these are pretty much standard. So you can open up your favorite book on nonlinear PDEs or semilinear PDEs, like my favorite is the Ladichenskaya book, and then you will find the precise conditions that you need to impose to get a classical solution which has these properties. These are what we need for our proofs to work. They're pretty much standard. Okay, strong, but standard, let's say. All right, and so now that we know that our solution of the PDE satisfies this kind of regularity, so it lives in what is called a parabolic Hölder space H3 gamma, then it makes sense that we assume that the approximating functions also come from that space, because we know we look for a solution in there, so our approximating functions should also live in there, and we take a bounded set for simplicity. More or less. Right, so I think these are reasonable assumptions. They are strong assumptions, but reasonable for what we want to do. And this is all I'm going to say about the approximating functions. So you'll not see any neural networks or any other approximating functions. We don't care too much about the details. Our work is more on this loss function. Does it actually work? What Reisi is proposing, and then you yourself are free to choose what kind of approximating functions you're using, as long as your class is bounded in this parabolic Hölder space. Our results will apply. Okay, now, next thing we need is a measure for the approximation error. And I claim that a very natural thing to do is this over here. So we are measuring the distance between a solution of the PDE and our approximating function evaluated along the forward process. Why is this natural? Because we know that this guy over here corresponds to the solution of the backward stochastic differential equation. So we are measuring the distance between approximating functions and solution of the BSDE. Yeah, so in fact, we are not learning the PDE, we are learning the solution of the BSDE, which is pretty much the same, but this is our point of view. Yeah, so we want to apply stochastic arguments, so we work even with the approximation error on the stochastic side of things. And this is in my opinion, is a very reasonable thing to do, because what kind of semi-linear PDEs do we want to solve? So my go-to example is something from mathematical finance. You want to compute the price of a certain option, which you can express in terms of a PDE, and your forward process will always be the price processes of your underlying assets. And then that's exactly what you are interested in. You want to know the price of the option, so the solution of the PDE evaluated along all possible realizations of your underlying prices. Yeah, so these are exactly the values that we are most interested in. Yeah, so in many ways, I think this is a very natural measure for the approximation error. Yeah, so along the forward process, we look for the error. And we can do so also the same thing also for the gradient. Yeah, we have to scale it by sigma, yeah, because this allows us to replace the gradient of the solution of the PDE by this Z component, and the second component of the BSDE, and then measure the distance between those, of our approximation and the true solution. These are our errors, yeah, and these we want to control, yeah, if we have a small loss function. And now comes the first convergence result, or the first convergence theorem. So these errors can be controlled by essentially our loss functional, yeah, plus a constant times h. Yeah, h, as a reminder, is the length of the time discretization. So this will go to 0 eventually. And so we control the error by pretty much the loss. The only issue is that in front of the loss, we have this h to the minus 1, which will explode. Yeah, so 1 over h goes to infinity when h goes to 0. This is very unfortunate. Yeah, this is a very bad thing. So this means that we have to hope, yeah, that the loss goes to 0 even faster, yeah, so that the right-hand side doesn't explode. Yeah, but the first thing, at least what we can do, is error is controlled by something times the loss function. In other words, yeah, in practical applications, you don't see the error, yeah, but you see the loss functional. Yeah, you can compute the loss function, of course. And yeah, if you see that it is small, then this means that also your error is small. Yeah, this is what this inequality here tells you. Yeah, so small loss means good approximation. This is a reassuring result for practical applications, at least. One remark, this does not depend on whether we choose our kind of loss functional or the original one by Reisi. The arguments are precisely the same and the results are also the same. Yeah, here everything still works. Yeah, it's just that Reisi's loss functional will not converge to 0 fast enough to kill that h to the minus 1 over here. That's why we had to make the adjustment. Yeah, but up to this point, the original loss function also works. And something which, well, mathematically I like, from a practical point of view, I don't like. This estimate is really sharp in a certain sense. So we cannot get rid of that h to the minus 1. It has to be there. And we even have a specific example where you can see that it shows up. Yeah, so in that sense, it is sharp. Yeah, so we look at a very simple PDE over here. This is even first order, time derivative, space derivative, and it has a very simple solution which doesn't even depend on the spatial component. Yeah, so this is as smooth as you want it. And now, from the slide before, the error of our approximating function should be controlled by the loss. So what we need is the approximation. We need approximating functions. So something which kind of looks like u. U is a linear function in time, so we could approximate that by linear functions, by constant functions. So a reasonable approximation within that class of approximating functions could be a function which is constant equal to 1. This will hit the solution of the PDE at time capital T exactly, and then you have an error as you go back in time. And what is nice about this, you can compute the loss of that particular function precisely. It's just t times h. And you can compute the error as well. The error is just t squared. And if you plug everything in, t times h is equal to the loss. So you can replace one of the t's by h to the minus 1 times loss. So you get that the error is precisely h to the minus 1 times the loss. In that sense, our result is sharp. Given our assumptions in that theorem or conditions in that theorem, we cannot improve it. But we can learn something from that. This shows the shortcomings of our paper or of our approach. The reason why we cannot get any better results here is there's two reasons. The first one is the result is uniform for all approximating functions. If we go back, no matter which approximating function you choose, you will always have that estimate here. And we have not imposed any structure on the approximating functions. So of course we cannot do any better. But if you were to assume additional structure, additional properties on the approximating functions, maybe you can improve the results. Because in the end, we are not interested in arbitrary approximating functions, but just in the good ones. So there is room for improvement, but you need to put extra structure on your approximating functions. Right. Now, we can control the error by the loss functional. So what's next is we have to show that the loss functional goes to 0, or vanishes fast enough. And this is the second convergence theorem that we have. We can show that if you take an arbitrary approximating function, then the loss is bounded by constant times h squared, and constant time, times the distance between approximating function and solution of the PDE. Meaning that if there is a loss function, let's call it u star, which can be close to the solution of the PDE, then the loss will be very small. This is how to read this result over here. Again, this is a uniform result in the approximating function. So the best thing that we can do is measure or control the loss in terms of how good the approximating function is. Right? If it's a terrible one, then the loss will be large. So we need some kind of control on the right-hand side, which measures distance to the thing that we're actually looking for. Okay, what can we learn from that result? So as I just said, if there really is a function which is close to the solution for the PDE, then the loss will be small, because this guy here will be small. This is C12 distance. This one here will be small as soon as step size is small enough. So loss will be small, but if the loss is small, then the error is small by the first convergence theorem. So this tells you that if you find a good one, if you get, if you have a good approximating function, then the error will be small, which is kind of going in circles, but very reassuring. Another remark about what kind of distance we are using here. So this is uniform distance between small and capital U and all derivatives, so first order spatial time derivative and second order spatial derivatives. Uniform on the entire state space, which is time interval times RD. And of course, this can be quite large, right? For an arbitrary solution U of such a PDE. And that's not the kind of thing that you do in practical applications. In practical applications, you try to approximate not on the entire space, but usually you work on a compact subset of that. And we actually do that in the paper. So in the paper, we have a more refined statement of the theorem here, which controls the loss in terms of distance on a compact or a closed subset of RD in the spatial component. This leads to a couple of issues. So you need to be able to control the probability of leaving this set. So pretty much all I'm trying to say here is what I've written down on my slides is just a simplification to make it a little bit easier to read. There's a refined result which is more compatible with how you would actually choose your approximating functions, or with convergence result for approximating functions. I put it like this. I will talk about this in just a second to see why this is. Another thing here is really where the adjusted loss functional that we've written down comes into play. So the same result is not true for the original loss function by Resi. He will have a C times H over here, which is not enough. Okay, and here again, this estimate is sharp. And also for that, I have an example, so we cannot improve on that. And I think this is a very convincing example. This shows that there's really no room here whatsoever. So let's take a look at another very simple PDE, heat equation with a nice terminal condition, so that you have a nice explicit solution, which looks something like this. Sine of x and then some exponential in time. And now suppose that we are in the nicest situation whatsoever, namely that our set of approximating functions actually contains this function u. So the loss, the left-hand side will be 0. No, it won't. It's a loss. Loss is a discretization, so it won't be 0. But with kind of tedious computation, you can compute a lower bound on the loss. You can show that the loss of u is something constant times h squared. And for Resi, it's for this original loss functional, it's constant times h. This already means we can't do better. Even if we are in the nicest situation where the solution of the PDE is in the set of approximating functions, our bound on the loss cannot be improved. So we have a lower bound of constant times h squared, and we proved that an upper bound is constant times h squared. So it doesn't get better than h squared. Okay, and here we also see that the original loss functional has a lower order of convergence. Okay, and now all that you have to do is put everything together, the two main convergence results, and see what comes out. And this is then our main theorem of the paper. Now suppose that we can find a minimizer of our loss functional. Let's call it u star, depending on h. Then we can find a constant so that the error of that approximating functions is bounded by constant times h, and h to the minus 1, and then the minimal distance of your set of approximating functions from the solution of the PDE. And this is the best kind of thing that you can expect on the right-hand side. So this means that if we have a very nice class of approximating functions, then this minimal distance here will be very close to 0, or even 0. And then all that remains is c times h. We can also learn from that. We still have that h to the minus 1 in front. Even if, let's say, this guy here is 0. Yeah, so if we don't have that term at all, the best error that you can get is constant times h. Yeah, since this is a squared error, we have a order of 1/2, convergence order of 1/2. This also tells us how we should choose the set of approximating functions, at least abstractly. Yeah, we need that if we parameterize that in terms of step size in time, this infimum, so the universal approximation distance should be of order h square, because then the h square cancels with the h to the minus 1, and what remains is constant times h. Yeah, so this is what you should do. And so in practice, or in applications, what you do is fix your time step, h, and then you take your set of approximating functions, say neural networks, and you add so many neurons to it so that your universal approximation distance that you see here becomes sufficiently small. I think for certain neural network architectures, you can actually write down how many neurons or layers you need to get such approximations. So there actually are results which tell you how to do that, or how many neurons you need at least to get these kind of results. So that's reasonable, or it's doable, even in practical applications. The only thing which I'm hiding here is that in that situation, your set of approximating functions actually depends on the discretization. It depends on h. So you want to make the set of approximating functions larger as you make h smaller. And then it may happen that the constant that we have in front here actually depends on your choice of approximating function. But to a certain degree, you can actually enlarge that as long as the bound in this parabolic Holder space, h3 gamma, remains unchanged. So you can add more functions to your set of approximating functions as long as they stay in a nice bounded set in this space over here, and then these constants that you have showing up everywhere, they don't depend on your set of approximating functions. This allows you to increase the set of approximating functions with h, so that you can actually choose something like this. So theoretically, everything's justified. All right, I have a proof for that theorem because this is very simple, but there isn't really much to do. It's just plugging together the last two theorems. So I will skip the proof, I think, in the interest of time. You just chain together the last two results, and then you see it right away. You're just combining the two inequalities for the optimal, for the minimize optimal function. Instead, I want to do a couple of final remarks. One thing I have not talked about now during the talk is that we always have these constants showing up in our estimates, and what is nice, what is satisfying for us at least, is that these constants, they do not depend on the underlying space, on the state space on RD, on the dimension D. It doesn't show up anywhere. So at least in terms of minimizing this loss functional and getting a good approximation of the PDE, this can be done independently. This works independently well, the dimension of the forward process, or the dimension of the PDE. This is really nice. What is not so nice is that what shows up is the dimension of the Brownian motion. I'm not sure if that's really true in general, or if we're just have a suboptimal proof. But at least in our calculations, we couldn't get rid of the dimension of the Brownian motion, which is a bit unfortunate. Yeah, just not so nice. We hope that we can get rid of that at some point. but for now, the dimension of the Brownian motion plays a crucial role, which should be kept in mind. So this dependence on might be an artifact of our proof, and there's no general reason why it should be the case. So this does not mean that we have proof that we can beat the curse of dimensionality or whatsoever, because there are still a lot of additional approximations or additional things to take care of when we actually implement that, right? Because, for example, when you're choosing a set of approximating functions, here you want a good approximation, and this also depends on the dimension of the state space. So if you have a nice class which can approximate U in a way which does not depend too much on the underlying dimension of the state space, then one could argue that there's no curse of dimensionality here for this particular situation. But this is not the kind of way that we're pushing with our results. And one should be aware of that. All right. Another thing to mention is that the original loss function. Yes, of course.
Yeah, regarding this dependence on the dimension, right?
Yeah.
When you go and look at the estimate, and it has this best approximation from the space, this space, finite space U to the target function, as you increase the dimension, right? And you want to still get this approximability of H squared. This may introduce some kind of a dependent dimension on U calligraph to be able to achieve this kind of approximability, right?
Yeah. So exactly. So it's this inequality here which is the tricky one. So here typically C will depend on D. There are, however, it depends on how strong it depends on D. So I think there are a couple of results for, don't want to say the wrong thing, but I think you can, for example, if U is Lipschitz, which it is in our setting, and our calligraphic use or approximating functions are a suitably chosen class of neural networks, you can show that C does not depend exponentially on the dimension D. It does depend on D. Yeah, it has to. It usually always will, unless you have something trivial you want to approximate, but it's not exponential. Yeah, so there are situations.
Even if the constant does not depend on the dimension, what could blow up very fast is sort of the number of parameters that you need to describe the set U calligraph, right?
Yeah.
That is what can get you also, even if the constant is okay. Yeah.
Also a very nice point, which is the reason why I like this this kind of solver here, or this kind of approach that you see here, and why I don't like the other methods, because as I mentioned in the beginning, there are these methods where you do it like we do. You split up your time. So T1, T2, T3, T4, and this is T5. And then the classical methods, or the ones that are usually used, they use one neural network for each point in time. Here, here. Yeah, so we have U0, U1, U2, U3, U4, and so forth. Yeah. And they have very nice convergence results. Yeah, it's very simple, or comparably simple to prove convergence results here. But you see that now if you make H smaller, the number of neural networks that you need actually explodes.
Of course.
Yeah, for us, it's the number of neurons and possibly layers, which explodes. Of course, it has to go to infinity because we want to get better and better approximations. But here, the complexity is much, much higher because you need both larger and larger neural networks and more neural networks. Yeah, so this is the advantage of this loss function that Reisi proposes, and the reason why we had a look at this, because to me this is more natural. Yeah, and the others are kind of hiding that you need so many neural networks and so much memory to store all of that. There's hidden complexity in there.
Sure.
Which is not to say that these don't work. I think they're even more efficient usually because dependence on time is usually very flat. But conceptually, I like this a little bit better.
Thank you.
Okay. Yeah, as I mentioned, the original loss function, the problem is just that we end up with a constant which doesn't go to 0. Yeah, because the loss function doesn't go to 0 fast enough. So with our methods, this doesn't work. This does not mean that this approach that Reisi proposes doesn't work, because everything that we do was uniform in the approximation function. So there's room for improvement. So we have not established that what he does is not working. It is working, at least in practice, and we have reasons to believe that our results can be improved to a certain degree, but you need additional structure on the approximation functions. And oh yeah, many open problems. As you can imagine, this is just the first step. This is us dipping our toes into this business of deep learning for PDEs. And there are so many things that you still have to consider. We just analyze essentially the loss function. Does the loss function go to 0 fast enough so that the error goes to 0? But of course, in applications, you need to do much more. You actually need to optimize the loss function, which is not a simple thing to do. We just assume that we have a minimizer or something which is close to the minimum. So we ignore that completely. We didn't say anything about choice of approximating functions. There are a couple of results which we could apply directly, which would help us, where you can be very specific, but we don't really care what kind of approximating functions to choose. As long as they're good enough, this will work. This is our message. Then there's a Monte Carlo error. Of course, you cannot compute the expectation, but if you do it on a computer, you have to approximate that using Monte Carlo. You make an error there. And what we are working on at the moment, this is for us the most interesting thing right now, more general PDEs. So we have one project going on where we do quasi linear PDEs, where you have fully coupled forward and backward stochastic differential equations. We work on variational inequalities or precisely reflected VSDEs. So we want to solve optimal stopping problems eventually with these kind of approaches. And we are quite active and try to see if our strategy of getting to these convergence rates can be extended to more general PDEs. And that's pretty much it. It's quite slow. Apologies for taking so much time. So if you want to have a look, the paper is on SSRN with much more details. I'm happy to answer any questions that you might have. Thank you.